Okay, today we're going to be talking about polar graphs. And in addition to the standard graphs we have here, I have some super secret notes that are not taught by other people. So you'll want an extra sheet of paper later. In your calculator, if you were to go to the mode button and look at your calculator, and I'll pull that up on mine, you will see that there are 4 different modes you can be in. You can be in function, which is like our y equals something x, blah, blah, blah. You can be in sequential, which I think is the last one in the mode. And you can be in parametric, which we talked about last time we were together. And you'll see POL, which stands for polar. And if I were to select polar, you will see an R. And last time we were together, when we were talking about polar equations, I told you you always had to get it in R equals, and this is why. So you can enter it into your calculator if you want to see a graph. Okay? And we can talk more about that later, but I just want to make you aware of that on your calculator. Polar. So one of the important things about doing polar equations is to know your unit circle really well, which we have memorized. So as I go along, I'm going to fill in some chart stuff. This is from my information that I know from my unit circle. And what we want to do is we want to look at this graph, r equals 2 times the sine of theta. And so what I'm going to do is I'm going to plug some values in, knowing that I'm looking for this r equals, I'm going to write it down right above the table here, r equals 2 times the sine of theta. Remember that theta is representing your angle. So in my chart down below, I'm talking about the sine of all these degree or radian measurements. So I go look at my unit circle. Now, maybe I don't have everything memorized, but there are a lot of them that I know right off the top of my head. Like, for example, at 0, the sine, which is talking about the y value, the sine is 0. So 2 times 0 is 0. I know that also happens at pi and at 2 pi. And I know the sine is 1 when I'm at pi over 2. And I know it's negative 1 at 3 pi over 2. So here are some ones I can fill in just like that, super fast. I also know, now something's wrong already. What did I do wrong already? You have to double it. Why? Because it says in the equation 2 times the sine of theta. So this was actually supposed to be a 2, and this is actually supposed to be a negative 2. Don't forget to double it. Okay? Don't forget, there's a 2 there, so you have to double it. I also know that every pi over 6, the sine is 1/2, right? From our unit circle. So if I double that, that's going to be a 1. So at every pi over 6, I'm going to have a 1. And now I just have to remember, is that positive or negative? And the sine is negative in the 3rd and 4th quadrants. So that means after pi, I'm negative because I'm below the axis. And then the only 2 that are left are the pi over 3s that are actually in the 1st and 2nd quadrant. And the coordinates there are the square root of 3 over 2.
It just means it's a root 3.
Well, exactly, Joe. Very good. It means it's just the root 3. So this one is root 3, and this one is root 3. Now for those of you who don't know, and you might not, root 3 is roughly, I think, 1.7. And so now I go in my table and I'm like, okay, we learned how to plot these points earlier in our unit. So the degree measurement means where am I facing? I'm standing at the pole, so here I am at the pole. I'm standing right here. And I'm facing in a direction and I walk out the radius. So at 0 degrees, I don't go anywhere. So I'm right here on the pole. At 30 degrees, which is the same as pi over 6, I walk out 1 unit. So at pi over 6, I walk out 1 unit. At pi over 3, which is 60 degrees, I walk out 1.7 units. At pi over 2, I walk out 2 units. At 2 pi over 3, I walk out 1.7 units. At 5 pi over 6, I walk out 1 unit. And at facing pi, I'm back to 0. And then look what happens when you go to 7 pi over 6. Look up for a second. Don't worry about writing down dots. So now I'm facing at 7 pi over 6, which is right here. Here's 7 pi over 6. And it says I'm supposed to walk -1. What does that mean?
Walk backwards.
Walk backwards. So I'm facing this way, and I walk backwards, and what happens? You're overlapping. You're on the same point you were at pi over 6. So basically what this is saying is that you're repeating your process. You're just facing in a different direction when you plot the points. So this is what it looks like. And you'll learn more about this in our super secret notes. What is that?
Circle.
It's a circle. It has a diameter of 2 units. Okay, let's move on to number 2 and try a different kind. So in number 2, this, first of all, let me back up. We're going to talk more about what these graphs are. So what I want you to notice in this one is it's 2 and then a trig function. All right? In the next one, there's some important information that you need to know in this box. You can read this on your own later. I'm not going to read it to you. Try and plug in some numbers and figure out what it means. But I'll talk about it in the context of our problems. Look at number 2. In number 2, they have r equals, and what's different between number 2 and number 1? It has a constant in there that's not necessarily in front of the trig thing. See the plus or the minus? This is going to produce a different kind of graph. The kind of graph that this produces when there's a constant plus or minus some trig function is called a limicon. And that's not really maybe super important that you know the exact name of that thing, but I just want you to know it's a different looking kind of graph. Now, we've already talked about from our unit circle how we figure things out. So what I'm going to do is I'm going to write down some numbers in the table based on knowing my unit circle really well. You're going to copy them down, and then I'm going to talk about graphing them. So here we go. You can type these in your calculator, or you can memorize your unit circle, or both. So here are the numbers I get. I get the numbers 2, 1, 0.27, 0, 0.27, 1, 2, 3, 4, 3, 2. Okay, so as you're comparing notes, I'm just going to quickly graph this. At 0, when I look at 0, I'm going to go out 2 units. So I'm facing 0 and I go out 2 units. I'm right here. At pi over 6, I go out 1 unit. At pi over 3.27, ooh, that's pretty tough to see maybe. At pi over 2, I'm at 0. And then it's symmetric. So 2 pi over 3, I'm at 0.27 again. And I have really big fat dots here, so that's not so great, but whatever. Pi over 6. Pi over 6, I'm at 1. Whoops, I hit the wrong one, didn't I? No, I didn't. Pi, I'm at 2. 7 pi over 6, I'm at 3. 3 pi over 2, I'm at 4. And then symmetric again. Please stop making those noises. Thank you. And it looks something like this. And that's called a limicon. Sometimes your limicon will look like that, but be a little bit different. It'll look like this. And I'll have a little hole inside. So those are the 2 different kinds of limicons. So sometimes it'll look like this, the blue on the right, sometimes like the orange on the left.
Wait, were you saying it's hard to remember last time?
Number 3, whenever you see a graph that looks like r equals, that's just going to be a circle with the radius, whatever they tell you. So in this particular case, this is my graph. So anytime you see r equals, it's a circle, and that's the radius. Number 4, anytime you see an angle, theta, equal to something, you just draw a line along that degree measurement. So this is a line. So theta equals anything is a line. Just find the whatever angle they're talking about and draw a line down that axis. Okay, so I'm going to jump to number 6 now, and the reason I'm jumping to number 6 is because it's also a limicon. And you can tell it's a limicon because as you look at the equation, you see a plus or minus in between the constant and the trig function. And so I'm going to go and look at how to graph this thing. We've already done one of these. So I'm just going to give you the coordinates down below, and then we'll graph it. So the coordinates that I get for this particular limicon are 3, 2.7, you can verify these later, 2, 1, 0, negative 0.7, negative 1, negative 0.7, 1, 2.7, and 3. As we're graphing this, though, I also want to point out, as you look at these coordinates, there are some coordinates that are missing. Do you guys notice that?
Yes.
Which ones are missing?
Power 3.
Yes, and?
Power 4.
All the pi over 4s are not there. So sometimes they'll provide a table for you that has pi over 4 information, sometimes pi over 3, sometimes something will be missing. Fill out whatever they give you. Okay? So now let's look at how to graph this thing. Is there anybody still copying those coordinates? All right. If I graph this, and I look at these coordinates, the first one at 0, when I face 0, I walk out 3 units. So 1, 2, 3, here's a dot. And then I go to pi over 6 and go 2.7. And again, I'm trying to get as close as I can. At pi over 3, I'm at 2. At pi over 2, I'm at 1. At 2 pi over 3, I'm at 0. So I'm standing on the pole, looking at 2 pi over 3, but I don't go anywhere. At 5 pi over 6, I'm at negative 0.7. So here's 5 pi over 6. I'm facing in the second quadrant, and I go backwards 0.7. At pi, I go backwards 1, so I'm facing 180 degrees, and I go backwards 1 unit. At 7 pi over 6, I go backwards 0.7. At 3 pi over 2, I go down 1 unit. At 11 pi over 6, I go 2.7. And then at 2 pi, I go out 3 units, and I'm starting to repeat myself. And so this is what it looks like. And this is kind of a limicon on its side. And it has that little hole in the middle like we talked about earlier in that orange diagram we had. So in your calculator,